Hello everyone, I am Anis from the Stat Department of Fractions. Today we will discuss the problem of the day 5. The problem states that there is a unit circle, hence we have the radius of the circle r as 1, and we are picking 3 points uniformly from on the circumference of the circle. The 3 points can be denoted as say x1, x2 and x3. We are to find the length of the arc which contains the point 1, 0. That is, if we are chosen 3 points as over here, say 1, 2, 3, then we are to choose the length, find the length of the arc which contains the point 1, 0, which is the following length in the figure. This is length L from here to here. Now, the first thing to note is that when we are choosing 3 points uniformly, the points can be parameterized by the angle they make with the center and they make with the positive direction of x-axis. For example, this point over here, if we connect it to the center and measure the angle in the positive direction of x-axis this ways, then this one is the smallest of the 3 angles. Similarly, this one is the largest of the 3 angles chosen. Hence, the points we are choosing on the point, they correspond to the angles chosen. That is, we can say that x1, x2, x3 are identical and they are chosen independently from the distribution uniform from 0 to 2 pi. 0 corresponds to choosing the point 1, 0 itself. We increase to 90, 180 and all the way up to 2 pi. Which is again choosing the point 1, 0. Observe that this length, which is in the middle, does not affect the length of this L as long as it is in the middle of these 2 points. Hence, the length of the arc is depending only on the length of the smallest angle. The smallest angle can be denoted as the first ordered statistic, which is x1, and the largest ordered statistics, which is x3, since we have 3 points. Explicitly, the length of the arc can be written as this angle plus this angle into the radius, which is 1 here. Now this angle is clearly x1 as per our notations, and this angle is 2 pi minus x3, since we are measuring direction with positive direction of x-axis. Times the radius, which is 1, hence we are omitting that. Observe that this length L is a random quantity and depends on the value chosen for the x1 and x3 ordered statistics. But though we cannot find the actual length, and explicitly we can find the expected length. By linearity of expectation, we have expectation of L to be expectation of x ordered statistic 1 plus 2 pi, which is a term free from randomness, hence and brought out of expectation, and expectation of x3. Hence, observe that once we know the expectation of x1 and x3, the expectation of L can be calculated easily. At this point, we make the observation that since x1, x2, x3 are from uniform 0 to 2 pi, we can scale them by dividing by 2 pi. x1, x2, x3 by 2 pi, so that they become IID from uniform 0 to 1. With this transformation, we can now calculate the expected value of the first ordered statistic using the fact that the kth ordered statistic of the uniform distribution, say y1, y2, yn, are IID from uniform 0, 1, then the kth ordered statistic, which is the y brackets k, follows beta k comma n plus 1 minus k. Here we can take y1 to be x1 by 2 pi and y2 to be x2 by 2 pi, and similarly x3. Based on this, we can calculate the expected value of x for statistic 1. Using this theorem, hence we get expect x1 x ordered statistic 1 by 2 pi. This follows beta k is 1 and n is 3 plus 1 minus 1, which is 3, and x ordered statistic 3 by 2 pi. This follows beta 3 comma 3 plus 1 minus 3, which is again a 1. Using this, we can calculate the expectation as expectation of x1 by 2 pi by the expectation of beta, which is 1 by 1 alpha by alpha plus beta, which is 1 by 1 by 3. Hence we get 1 by 4 as this expectation, and expectation of x ordered statistic 3 by 2 pi to be 3 by 3 plus 1, which is 3 by 4. Next, we can substitute this value. Obtained for the x1 by ordered statistic 1 by 2 pi and expected value of ordered statistic 3 by 2 pi in the expression over here. Substitute it over here so that we get expectation of x1, which is 2 pi by 4, so which is 2 pi times 1 by 4, and again we have a 2 pi, so we add a 1, and expectation of x3 is 3 by 4 times 2 pi, so we can subtract a 3 by 4 over here, so that we get the answer as 5 by 4 minus 3 by 4, which is half, so half times 2 pi is pi. Hence we get that the expected value of the length of the arc to be pi. Now note that since we have used the following fact, we can provide an intuition as why this is true, though it can be proven mathematically. We provide the following details over in the next slide. Using this general result, which is that if x1, x2, xn are IID from F with the CDF capital F, then x ordered statistic I has the density given by this expression. This expression of f underscore x ordered statistic I. So this is the density of the ith order statistic. If you see the uniform distribution, then we have f of x, say x is IID from a uniform, then f of x is basically x indicator 0 less than x less than equal to 1, and fx, which is the density, is 1 for 0 less than equal to x less than equal to 1. Using this, the distribution of the kth ordered statistic, that is f x k of x, is in fact n factorial divided by k minus 1 factorial into n minus k factorial into f of x power I, which is simply x power k minus 1, into f of x, which is simply 1, and the last term is 1 minus x power n minus k. Observe that this can be represented as x power k minus 1, and we are adding an extra term. It's not an extra term, it's simply gamma k. Since gamma k is k minus 1 factorial, we can represent x minus 1 by k factorial. The motivation to do this is because we want to write this in the form of density, in some known density, specifically the density of beta distribution. Similarly, 1 minus x power n minus k can be written as n minus k plus 1 and minus 1, so that if we observe the non-constant term, the variable terms, we see that it is x power k minus 1, 1 minus x power n minus k plus 1 minus 1. Hence, this corresponds to a beta k comma n minus k plus 1. Let us see if the constant terms align themselves accordingly. So this term is gamma k. Since this is gamma n minus k plus 1, we need a gamma n minus k plus 1 over here, and we need to divide it by their sum, which is gamma n plus 1 for x less than 1. Observe that gamma n plus 1 is basically n factorial, hence it matches, and gamma n minus k plus 1 is n minus k factorial, and this matches, and gamma k is k minus 1 factorial, hence this also matches. Hence, in fact, this distribution f, this density of f on our statistic k is same as the density of beta k comma n minus k plus 1. This is the result we desire to prove, that the kth order statistic of uniform follows beta k comma n minus k plus 1. With this result in hand, we can quickly find the expectation as we have calculated over here and substitute it back to the expected value of L, so that we get the expected value of the length of the arc, which contains the point 1, 0 to be pi. Thank you.